Nós daremos início, portanto, em ato contínuo, à palestra internacional Inibidores migratórios de corrosão em concreto armado para novas construções, reparações e aplicações especiais, com Mrs. Jessi Meyer, vice-presidente da Asia MCI Additives Cortec Corporation. Possui bacharelado científico em Química, com ênfase em negócios pela Universidade de Wisconsin, na cidade de Eau Claire, e desde então ocupou posições de serviço técnico, vendas e atualmente é vice-presidente de vendas da MCI Asia, da Cortec, na Cortec Corporation, em St. Paul, Minnesota. Jessi ingressou na Cortec no ano de 2000 e tem mais de 18 anos de experiência em construção e restauração de construções de concreto armado. É responsável mundialmente pela linha de produtos inibidores migratórios de corrosão, MCI, e também coordena os negócios da Cortec Corporation na Ásia. Jessi possui 6 patentes no campo de inibidores de corrosão usados no concreto e na indústria da construção civil. Ela é autora de uma série de artigos científicos através das instituições ACI, NACE, ICRI, entre outras. Jessi já foi membro da diretoria do Instituto Internacional de Reparos em Concreto, ICRI, e atualmente é a representante de marketing do comitê. Ainda participa dos comitês de corrosão e durabilidade, vida útil. Já foi presidente do ICRI de Minnesota e atualmente está no comitê de comunicações. Além do ICRI, Jessi é um membro ativo do American Concrete Institute, ACI, e da National Association of Corrosion Engineers, NACE. Ocupa atualmente a cadeira do capítulo 13, Inibidores de corrosão, do documento de número 212, Aditivos para concreto, e participa de diversos outros comitês nestas instituições. Com a palavra, a palestrante Mrs. Jessi Meyer.
Thank you. Good evening. Thank you for the warm welcome. Tonight, I will introduce you to the amine-based migrating inhibitors and discuss all of the applications in which they can be used, which range from new construction to restoration, as well as specialty applications. Okay, so we will cover the chemistry of these inhibitors. We will go through how we determine their corrosion protection capabilities. I will show you how we can assess their migrating capabilities, as well as all of the applications which I just spoke: new construction, repair, and specialty. To understand how these materials work, it helps to understand how corrosion works. So we define corrosion as the destruction of metal by chemical, electrochemical, or electrolytic reaction within its environment. To understand a corrosion cell, it has 4 components, 4 main components. We have an anodic area. This is where we see the damage forming. We have a cathodic area where the charge balance is occurring. We have an electrolyte and electron transfer. And if we slow down or stop, any one of these 4 components, we can slow down or stop corrosion. Therefore, corrosion inhibitors are classified based upon which part of this corrosion cell they affect. And the chemistries which I am talking about affect both the anode and the cathode. So they can be referred to as mixed inhibitors. Let's see. These products are generally amine-based materials. Again, they affect both the anode and the cathode of the corrosion cell, and they shift the potential in the direction of the predominant reaction. Because these materials act on the steel itself, their dosage rates in concrete are very low. So generally, for corrosion inhibiting admixtures, they're dosed at 0.6 to 1 liter per cubic meter. Or if you're using a powder version, 0.6 kilograms per cubic meter. The topically applied materials are dosed about approximately 3.6 square meters per liter. So very good coverage rates. I'm gonna try, can we play the video that's associated? There's a video. Can you play? Okay. So here is a video demonstrating how these materials work. This bottle on the left is steel wool in water. And as you can see, it starts to rust very quickly. It would start to rust in the time that I'm talking to you tonight. But this is a time lapse done over 2 weeks. And what you notice, the bottle on the right is not rusting over the 2 weeks that it's exposed to the water. And that's because in this water, we added 20 drops of the migrating corrosion inhibitor technology. And so the amine-based inhibitor was added into this test bottle. What you can see is the rust is forming here, but also there's condensation up above, and rust is starting to form on the steel wool up above as well. There's no rust forming on the steel wool above the water. So what this is demonstrating is that these products actually have a vapor phase. They don't just have to be in the liquid or touching the steel to provide protection. They're able to provide protection as a vapor in the airspace above. Okay? Okay. When they are used in new construction applications, these products are generally added to the concrete mix at the ready mix facility. So they are evenly mixed into the concrete and dispersed throughout it. When they're used on existing structures, they are generally applied as a topical treatment to the surface of the concrete. And then these materials will migrate inside the concrete. The initial ingress into the concrete is as a liquid, so the concrete acts like a sponge, drawing the liquid inside. Once it's inside the concrete, the inhibitor can move as a vapor. As we just mentioned, it can move as a gas, and it simply moves throughout the concrete from areas of high concentration to low concentration, trying to create an equilibrium inside the concrete. The third way is when it actually encounters embedded reinforcing steel. When it encounters this metal, it actually has a physical attraction to it. So I say, think of this like a magnet on your refrigerator. It wants to stick to it. It's a physical reaction, and it tends to want to stay there. There also is not a lot of air exchange at the depth of the reinforcing steel, so these materials can last in the concrete for a very long period of time. Once they reach the metal, they tend to want to stay there. They don't migrate back out of the concrete. Does that make sense? Okay. It's the nitrogen or the amine in these chemicals that are responsible for their strong bond to the metal. And so a little bit on the chemistry of these materials. The first generation were based on amine alcohols, and the latest generation is based on amine carboxylate. And you see that both of these materials look very similar to each other, especially if you're not chemists. But what is important are these nitrogen groups here. So they have a lone pair that likes to stabilize themselves in the surface of the metal. So they absorb into the surface of metal, and then either the carboxylate or the alcohol groups stick away from the surface like a tail and interact with each other. And so this forms a molecular barrier on the steel that keeps water, chlorides, or other contaminants from reacting with the surface of the steel. Okay. The difference between these materials are that the first generation cut corrosion rates approximately in half compared to a control. The latest generation can cut corrosion rates by 5 to 13 times. So a much more dramatic reduction in corrosion current. These materials are evaluated for corrosion protection through a couple of different standards. The main standard that I have found globally is from the United States, and it is ASTM C1582. This standard actually encompasses many test reports within it. So one series of tests says that the admixtures will not affect the physical properties of your concrete. They will not affect strength, air entrainment, or setting time, okay? The second series of tests within it are actually testing corrosion protection in the presence of chlorides. So the main test that you can do is ASTM G109 or ASTM G180. G109 consists of making concrete blocks, like what you see here, with 3 rebar inside, and then they pond 3.5% salt water in the containers on top, 2 weeks wet with salt water, and 2 weeks dry. So each cycle is approximately 4 weeks. Essentially, they're waiting for the chlorides to get into the concrete and initiate corrosion on the top bar, and then they take a difference between the 2 bars and estimate the macrocell corrosion. The requirement is that to be a corrosion inhibitor, you have to not only reduce the rate of corrosion, but also have the same or higher amounts of salt inside the concrete. So what they're trying to prevent would be products that are only waterproofing. They want to actually show that your material is acting at the level of the steel. Okay. Then there is a modified G109. It is the same setup. However, to make the test run faster, they will do a saw cut in the center, apply a load so that a crack forms in the sample before they pond salt water, so that the salt water gets to the steel immediately and corrosion occurs faster. Okay? And then electrochemical techniques would look like this. There's a reference electrode. In the center would be a test electrode. And so they're running them in solution with the inhibitors inside. This is an example of the ASTM C1582 results for a normal set amine-based corrosion inhibitor. And so the test has 3 requirements that you have to meet to pass. The first is average integrated current. So the test is stopped once the control reaches 150 coulombs of charge passed. When that happens, the material being tested has to have a rate that is less than 50 coulombs. So you can see here the material that was tested had a rate of 29, which met the standard. So it had less than 1/3 the corrosion. Then they take the samples apart and actually look at the steel that was inside. So they look at the average corroded area, and the requirement is that the test sample have less than 1/3 the amount of corrosion that the control sample had. And so again, you can see this material passes. Finally, they have what is referred to as the critical chloride content. That means that when the control reaches 150 coulombs, the chloride level is calculated, and then a standard deviation of chlorides is added to it. And the treated sample has to have the same or higher level of chlorides in it to pass. So this is showing that your product is reducing corrosion in the same or higher level of salt in the structure. Here's an example of a G109 that was carried out much longer. So instead of a 2-year test, this test was carried out for 5 years. And it's designed to show you how the inhibitor acts over a long period of time. So in this case, the control initiated corrosion 9 cycles, or approximately 9 months into the test. And you can see that the corrosion rate goes very fast. And in fact, at the 51st cycle, the samples had cracked so badly that they had to stop ponding salt water on them because it wouldn't stay in the container. So the control sample was stopped at 51 test cycles. The migrating corrosion inhibitor did not initiate corrosion until the 18th cycle. So it doubled the time to when corrosion started, but it has a secondary effect. The secondary effect is that the corrosion rate is also dramatically slower once it starts. So what you can see is that 5 years into the test, the corrosion rate was still very, very low. So you can imagine the extension in service life that you can get from these materials in a concrete structure. This is an example of a cracked beam test. This particular test was done for the Illinois State DOT approval, so it was for our Department of Transportation approval, and it was required to test the organic or amine-based corrosion inhibitor in comparison to other technologies that are currently used. And so we were required to compare it to calcium nitrite technologies as well as an amine ester technology. And what you see here is the amine ester was dosed at 5 liters per cubic meter, the calcium nitrite at 20 liters per cubic meter of concrete, and the amine-based or organic inhibitor was dosed at 1 liter per cubic meter, and then no inhibitor. So this is the control. These are the other 2 materials that were already approved. They provided about 25% protection. But what you see here is the migrating inhibitor provided over 80% protection even when there were cracks. So this is a lab test, but it was also confirmed in a 10-year study test that I will show you in just a little bit. But the assessment for topically applied corrosion inhibitors is M82. M82 is a protocol that was developed by the U.S. Bureau of Reclamation, and it is a way to evaluate how repair products will work once corrosion has already started. So in this case, it's kind of like a large G109 test. It's very similar to the previous test that I showed you, but you see the samples are much larger. They're the size of a pallet, a shipping pallet, and they have 6 reinforcing steel that are embedded in the concrete that can be wired together to be continuous, but also separated to take individual corrosion rates on each bar by itself. And how this test works is similar to the G109, where they pond salt water on the surface, 2 weeks wet, 2 weeks dry. But the requirement here is that they wait until these samples are actively corroding until they apply a topical treatment to it. So once they are actively corroding, then you could do a repair. You could cut out a repair. You can test sacrificial anodes, or you can test topically applied corrosion inhibitors. So in this case, the topical migrating corrosion or amine-based corrosion inhibitors were tested on this sample. And there's 2 levels of corrosion that you can reach. So the first is waiting for these control samples to hit 5,000 coulombs. The second way is waiting until those samples hit 10,000 coulombs of charge pass. So that means they have double the amount of corrosion on the samples. And the reason you would wait until they hit 10,000 coulombs is because you want to show that your product works independently of chlorides in the system or at a higher chloride threshold. So all of the materials that we have shown in this case were tested at 10,000 coulombs passed, which means they work independently of chlorides in the structure. So with the control, these are the average chloride levels when the repair was done and at the end of testing. And what you can see is the control levels of chlorides increased dramatically from the time of repair, but all of the treatments, all of the amine-based corrosion inhibitor treatments had roughly the same amount of chlorides at the end of the test as when they were repaired, which meant they were keeping the ingress of chlorides out. And they were also reducing the relative humidity inside the samples. In this case, they also reduced the amount of cracking. So after repair, you can see the average length and area of the repair, both at repair and at the end of the test. And you can see that each of the treatments had reduced the amount of cracking significantly compared to the control. This is the corrosion current that is passed with each of the amine-based corrosion inhibitors. And what you can see, so time 0 means all of the samples actually reached 10,000 coulombs, and then they stopped ponding the salt water and let the samples dry out before they did the repair. So time 0 is time of repair. And what you see is the control hits 10,000 coulombs as soon as they start ponding salt water again, which is where it was before, and then the corrosion rate continues to increase dramatically over the next 6 months. The treated samples all reach the 10,000 coulombs where they were before and don't exceed it. So they tend to stay there, which means they have reduced the corrosion current about 95% in this case, in the repair. And so you can imagine the length of repair that you would have with a topical treatment. Here's another example of corrosion testing that is done on topically applied inhibitors. This is also referred to as a modified G109. And in this case, the samples were kept submerged in salt water for 400 days. And at the end of 400 days, they were confirmed that the inhibitor had not only reduced the rate of corrosion, but they also did what we call XPS and SEM testing. And this is testing that was done on the reinforcing steel that was removed from the samples to show the actual film the inhibitor formed on the embedded reinforcement. So they were able to show the inhibitor went from the surface to the steel and formed its film. So during this test, we tested both high-density concrete and low-density concrete. The low-density control is this line right here, and the high-density control is this line right here. And you can see all of the treated samples, both high and low density, were much higher than either of the control samples. So they did not lose their resistivity to corrosion over time. And then the XPS analysis analyzes all of the different chemicals found on the surface of the metal. And so what is showing here are typical chemicals that you would see on reinforcing steel that's come out of concrete. Iron, oxygen, chlorides. Most concrete does not have amine in it unless it's been added to it from some sort of an admixture. So generally, amine-based corrosion inhibitors would increase the level of nitrogen in your concrete. So if you're looking at the untreated sample, you see it has a fairly low level of amine on the surface of the metal. But what you see is on the treated two samples, it increased by 5 times. So that is showing you that the inhibitor went from the surface of the concrete to the reinforcing steel and formed a film by the concentration that's left there. The other way that we can show that these inhibitors migrate into the concrete is through UV methods. So UV mass spec or direct analysis real time, which we refer to as DART. So DART takes a picture of the surface of the metal as well and shows us that the inhibitor has reached that level of concrete. Okay, so I'm sorry, I thought I had one more slide there. So for new construction applications, advantages of using amine-based corrosion inhibitors are, as we discussed earlier, that they have a very low dosage rate. And because they have a very low dosage rate, you don't have to make any adjustments to your concrete mix design. You don't have to reduce the mixed water when you add them. They also work even in cracked areas and have been tested to meet the ASTM C1582. They can be used together with high-performance concrete. So when you use them with silica fume, fly ash, slag, or other pozzolans, they don't make the mix any harder to work with. Some other types of corrosion inhibitors make the concrete sticky and hard to finish when you add them together with these materials. You do not tend to see that with the amine-based inhibitors. There's generally no effect. 2 other advantages are that these products can be used together with cathodic protection. So if you have cathodic protection in one area of your structure, but not in another, these products can be used together with it. And finally, the latest generation of amine-based corrosion inhibitors are actually derived from corn. So they come from a bio-based resource, a renewable resource, that is also has very low toxicity, which means this approval means they can be used in structures that would hold drinking water. And they have been used in many structures that hold drinking water. So they're very safe, they don't leach out of the concrete or hurt people if they're used in drinking water structures. Okay. These materials as admixtures have been used for more than 30 years. This case history is the oldest case history for the amine-based corrosion inhibitors. It is a bridge based in St. Paul, Minnesota, that was treated in 1986. And the unique thing about this bridge is it was part of a federal government study when it was started. And so the westbound lanes had inhibitor and the eastbound lanes did not. So it was a repair to the bridge deck where they took off the top 7 centimeters of concrete and put a new overlay down to repair it. The overlay was exactly the same on both sides, except the westbound lanes had the amine-based inhibitor added into it. And then this bridge was studied for more than 20 years. So we used devices to do half-cell potential readings and also actual corrosion rate readings on the bridge. The mixed design, as you can see, the eastbound lanes were the control, westbound lanes were the treated. The only difference is the addition of the amine-based inhibitor. And you can see it was approximately 0.6 liters per cubic meter is the dosage rate. The average chloride levels over the years were also taken at different depths, so 0 to 2 centimeters, 2 to 5 centimeters, and 5 to 7 centimeters. The reinforcing steel was located at 7 centimeters, so that's the significance of measuring to 7 centimeters. And so in 1991 and 1992, the federal government took these readings. In 2000 to 2011, the manufacturer of the material and the Minnesota Department of DOT did updated readings. And so what you're able to see here, when the bridge was first constructed, first repaired, there was very little difference between the two sides. So this was a high performance concrete mix. It was 0.32 water cement ratio. It had 3% silica fume. And the only exposure to corrosive things in Minnesota are de-icing salts. So it took a very long time for the de-icing salts to reach the steel and actually initiate corrosion. And so what you see is at the beginning they look very similar, but when we get out to 2011, which is almost 25 years after treatment, the control side entered active corrosion. And so now you can see the control side has much higher levels of corrosion than the treated. So this is half-cell potential, and this is the actual corrosion rate. So with the actual corrosion rate, you see here in 2007 and then 2011, when corrosion initiates, you see how much more dramatic the corrosion current is with the control versus the treated. Follow-up readings were done on this bridge in 2013, but by 2013, the control side had actually delaminated. And so the readings were not valid. And in 2015, the entire control side was removed and replaced. The treated side was not. So the treated side is still in place, but we can't do comparative readings any longer because the control side has been repaired. Okay. New construction applications, these materials are actually used very widely in the Middle East region. And so this is an example to show you how much they cost in a real-life example. This building right here in the center is Princess Towers, which is located in Dubai, and until recently was the tallest residential building in the world. It is 101 stories tall, has 107 residential floors, with 763 living units inside. The chloride levels in the groundwater in this location exceed 90,000 milligrams per liter. It's the highest level of chlorides in the world. And they wanted a 100-plus year design life on the building. So the cost to construct the building was more than 188 billion US dollars. The cost to add the amine-based corrosion inhibitor into the substructure where the chloride exposure was only 136,000 US dollars. Service life analysis of the concrete without the inhibitor was estimated to last 48 years before repair. After adding the inhibitor, service life was estimated at 103 years. So for less than 0.1% of the entire project cost, you doubled your service life. Now, what does that mean over the life of the building? Well, if the building actually lasts 100 years and we take into account the revenue from the residential units inside, and then we subtract out building management, licensing fees, all of the fees that we would, insurance, those sorts of things that we would have to take off, we can calculate a net profit per year on this building. So we estimated that at year 1, they're going to get 9.8% return on their investment. At year 10, they'll be at 12%. And by year 48, which is the control sample, they will have a 27% return, and the present value would be $12 million in revenue. So if they had the original concrete, they'd have to start repairing here, and they would have additional maintenance costs. But by adding the inhibitor, we're saying they're not going to have repairs until 100 years, which means their return on investment will be over $1 billion compared to the 48-year return on investment. So you can see how much more money they're making for less than 0.1% investment at the beginning. Okay? When I mentioned the cracked beam study had been confirmed in real life, this is that confirmation. So the Vachon Bridge is located in Montreal, Canada, and this was a study done by the National Research Council of Canada. And they tested the amine-based corrosion inhibitors alongside 10 other materials in concrete. So they tested black steel in the bridge, they tested epoxy-coated steel, and then several other types of corrosion inhibitors. And at the end of 10 years, they ranked a calcium nitrite dosed at 20 liters per cubic meter, number 1, and the amine-based corrosion inhibitor dosed at 0.6 liters, number 2. But the significant difference here was anywhere there was cracking, the amine-based inhibitor performed the best of all methods tested. So if you have any cracking in the future, this is the material that would perform the best. So what you can see is this is the rate of reinforcement with no cracks. Span 21 is the control. Span 12 was epoxy-coated reinforcing steel. And then all of these letters were the tested inhibitors. So letter F is the amine-based corrosion inhibitor, and letter H was the calcium nitrite-based corrosion inhibitor. Now what you see where there was no cracking, all of the materials performed similarly. But where there was reinforcing steel, of all of the products, the amine-based inhibitor was ranked number 1, which means it had the lowest rate of corrosion. And the calcium nitrite-based inhibitor was actually ranked number 6 and very close. It's actually slightly higher readings than the control. So again, this was a 10-year study. Anywhere there was cracks, the amine-based inhibitor outperformed all of the other products tested for corrosion. This is a hotel structure that was just completed in Alabama, located right on the coast. And originally, the owner was going to use epoxy-coated steel in the structure. And so service life analysis showed that the concrete by itself with black steel would have 11 years until the first repair. When we use epoxy-coated steel, we received 25 years until first repair. If we add the amine-based corrosion inhibitor, we have 40 years until first repair. In addition to providing the longest service life, the amine-based corrosion inhibitor actually gave them credit for LEED on this project. So does everyone here know what LEED is? Yeah, environmental design credits for the US, so it means you're using renewable resources, okay. So with the amine-based corrosion inhibitor, it has 67% bio-based content. So they were able to get LEED credits for this. And in this case, it was also manufactured within 500 miles of the job. So they got additional points for purchasing a material that was manufactured nearby. It was important to them because this area of the Gulf is very restricted due to environmental concerns. So they don't want any products being used that could hurt the environment in the ocean near this structure. And so the certification for use in potable water was very important. They also had a significant cost savings. So the migrating corrosion inhibitor, compared to the epoxy-coated steel, saved them almost $750,000. So using the migrating inhibitor instead of epoxy-coated steel. And then comparing that to using a calcium nitrite product for the ready mix supplier, it meant much less inventory that they had to keep on hand. So to use the amine-based inhibitor, they only needed 937 gallons of material. I apologize, that's not translated to liters. But they would need 30,000 gallons of the calcium nitrite-based inhibitor to provide the same protection. So you can imagine transport, costs, storage fees as well. Okay? Another interesting application is in the bases of wind turbines. So in this situation, these turbines are located in the coastal area of Texas, where the groundwater has high levels of chlorides. And they have concerns because there's so much reinforcing steel, and the motion of the wind turbine can cause cracking in the concrete if it's not constructed properly. And so the migrating-based corrosion inhibitor has been used in quite a few wind turbines in the bases as well. So this is just trying to give you an idea of the wide variety of applications where the products can be used. Moving on to restoration, probably the most prestigious case history that we have done with these materials is on the Pentagon in the United States. This project was a 10-year construction restoration project. So it was treating all of the interior light wells between the rings of the Pentagon, and it was cast in place concrete that was going to take the contractor 10 years to finish. So it required a 20-year warranty. They didn't want to have contractors in the building perpetually. This structure was carbonated to more than 7 centimeters depth. So all of the corrosion here is due to carbonation. The repair started in 2003 and was finished in 2012, and consisted of using the amine-based inhibitor in repair mortar and the patches, as well as a topical treatment, followed by a silicate and a silane coating that was used to keep further carbonation out, but also to match the aesthetics of the building. So the requirement was that someone sitting in their office on this side, if they looked out the window, they should not see the repair on the opposite wall, because it's a historic building that required the repair to match what it looked like. So there's more than 300,000 square meters of patching and repair done here. This is what it looked like before repair. You can see a lot of damage. This is the repair patches, and then after treatment with that silicate and silane coating. So you can see the color was matched, and all of the repairs were blended in. During the entire restoration time, the amine-based corrosion inhibitors were tested every 6 months to show corrosion rate readings. Because the coating that was placed on top made it impossible to take corrosion rate readings, sections were left where there was no coating, and then wires were run from the reinforcing steel so that we could make connections to do actual corrosion rate readings. So every 6 months we would return and show what the readings were. The device that we used here is called a galvapulse, and the galvapulse has requirements for time to visible damage. And with the galvapulse, anything that is more than 15 micrometers per year is considered less than 2 years to visible damage. So you can see what it looked like at the beginning. There was definitely visible damage. This is the corrosion rate reading before repair in one section. This is the corrosion rate reading after repair. After repair for the next 10 years, this reading never went above 5 microamps per centimeter squared. 5 microamps per centimeter squared or less means there's more than 10 years to visible damage. So they knew after 10 years that they would have at least 10 more years before they would have visible damage on this building. We're now in 2018. The project started in 2003, so we are 15 years in. There's currently no visible damage on the building. So it's still meeting the requirements of the warranty. This is with the consortia, the Water Association in Tarragona, Spain. And they have over 7,000 square meters of pipeline repair that was done. and 13,000 square meters that were treated with a topical treatment of corrosion inhibitor. These pipelines carry the drinking water for the entire province. And these were treated in, I believe, 2009. So they have been in place for 9 years with no damage. This is an example of using the amine-based corrosion inhibitors together with a water repellent. So you have a 2-in-1 product. And in this case, it's the Francis Scott Key Bridge, which is in Maryland in the United States. It was treated in spring of 2008. It is now 10 years old with no new reapplication and is still performing very well. So what I'm trying to show is that these products have longevity and have been tested for many years. So while they are new to Brazil, they're not actually new in repair or new construction. Moving on to specialty applications, this is an example of reinforcing steel in Dubai, and this is from 2009. So if any of you remember, in 2009, Dubai's market crashed, and a lot of the construction stopped. So they had a lot of buildings that were half constructed with reinforcing steel sticking out that were left. So you can see the condition of the reinforcing steel that was sticking out on this structure. And it was treated with a rust converting primer together with a topically applied temporary material that contained the amine-based corrosion inhibitor. The picture on the right was taken 2 years after application. These were left outside in the UV, in the sun, with salt exposure from the air. And you can see there's no new corrosion on that reinforcing steel. And the advantage of the materials used here is that they did not have to be removed when construction started up again. So they were able to place concrete around it without removing the materials that had been applied. Another application of these materials is in temporary protection of post-tension bridges. And so in the United States, there is a requirement that if post-tensioning is put into the structure and sits for longer than 14 days, it's required by law to be protected by a corrosion inhibitor. These materials are able to be fogged into the duct as a powder, and it's really easy. They just tape the ends with duct tape. They can sit up to 2 years and provide corrosion protection. So in the case of this bridge right here, it's in Illinois. The inhibitor was fogged in. It sat for 4 months through snow, rain, ice, through our winter. And in the spring, they pulled out 50% of the strands, and they had zero corrosion, even though there was water inside the ducts. The advantage of these products is they don't have to be removed before you put grout inside. So they are easy, and then they also have the approval for contact with drinking water. So if they do happen to spill into the waterway, they aren't going to kill any of the fish or other wildlife. Another example is repair of post-tensioning structures. So this is a post-tension structure in Alabama that had voids in the grout of the post-tensioning. And so you can see where those voids were, there was heavy corrosion. And so a new grout was injected inside of the duct, and the new grout contained the amine-based corrosion inhibitor. The amine-based corrosion inhibitor has been able to reduce the rate of corrosion and has been in place since 2003. So we are now 15 years out and reducing the corrosion on this bridge. Cable stay bridges. So in this case, the inhibitor was injected into the dehumidification system that was being used to protect the bridge. So even though the dehumidification system was turned on, they were still experiencing strands that were breaking. And so a lot of research was done to put the amine-based inhibitor through the dehumidification process, which carried it through the entire length of the bridge. This has been in place since 2008. The inhibitor has taken strand breakage to 0, and it is still constantly monitored. This is an example of the test setup that they did for this bridge prior to applying it. So they set up very high-tech samples and determined how far the inhibitor would migrate through the ductwork with the system. And then they used acoustic emissions to test the strand breakage inside the ductwork. So these inhibitors have been used, again, for more than 30 years in multiple applications. Their effectiveness has been demonstrated both in lab and field testing, and they can effectively increase the service life of your structures, whether they're new or repair. So with that, obrigado. Any questions?
Nós convidamos agora que retorne ao palco nosso presidente do IEP, José Rodolfo de Lacerda, para que proceda a entrega do certificado de participação e a presença aqui no nosso evento, a Mrs. Jessi Meyer.